All right, so now that we've talked about the definition of a log and how to evaluate a log, let's talk about how to graph a log. Logs and exponential functions are inverses of each other, so let's illustrate that and use that information to graph. So let's graph this base function here. This is the exponential function. Hopefully you don't have to always make a table to graph these, but when you're first starting out, maybe you do that a couple times. You know, what is 2 to the first power? 2, I'm sorry. Well, it is, but what's 2 to the 0 power? 1. What's 2 to the 1 power? 2. And then maybe let's do 1 on the other side. What's 2 to the negative 1 power? 1/2. And we should know that it looks like exponential growth, on the right side, exponential decay on the left. Decays to 0 on the left, grows exponentially on the right. Okay? Find the domain and range. So the domain of f is all values of x, so negative infinity to positive infinity, all reals. The range of f would be, the y values. Y goes from, the first y value is something bigger than 0. So 0 is the bound, but it's not equal to 0, so x goes to 0 to infinity. So let's graph and talk about the domain and range of the inverse of x. So just from a review from our previous lesson on inverses, remember the theme was always kind of switching the x's and y's around, right? So if I know the domain of f is that, then I know the range of f inverse is this domain, so all reals. And if I wanted to find the domain of f inverse, that's going to be equal to the range of f. You switch the x's and y's, you switch the... So this point here, which was 0, 1, is going to become the point 1, 0. Switch the x and the y. 1, 2 is going to become 2, 1. Negative 1, 1/2 is going to become 1/2 negative 1. My exponential function has a horizontal asymptote of y equals 0. Therefore, the inverse is going to have a vertical asymptote of x equals 0. Switch the x and the y. This function grows extremely fast. This function here is going to grow extremely slow. And if you recall, a function's inverse is simply a reflection of that function along the line y equals x. So this is the inverse of 2 to the x. Now at the beginning of the lesson I said exponentials and logarithmics are inverse functions of each other. Well, how do we know that? Well, let's prove that. Solve it algebraically, or find the inverse algebraically. So y equals 2 to the x. This is my base graph, my starting function. To find the inverse algebraically, you switch the x and y and solve it for y. Now, unfortunately, we haven't really learned how to solve logarithmic functions yet, not technically, but let's just try to write this in logarithmic form and see what happens. Log base 2, the exponent goes here, and the x goes here. So I just want to point out to you that whenever I rewrite this in logarithmic form, I actually solve that equation for y. This is my inverse function. Log base 2 of x. So what does that tell us? The inverse of 2 to the x is log, I'm sorry, that's not an equal sign. Don't do that, don't write that down. The inverse of y equals 2 to the x is y equals log base 2 of x. The graph that I just drew is a graph of the log function. So where exponential functions always cross at 1 on the y-axis and increase really fast with the horizontal asymptote, log functions are going to look like this, and they're going to look like that. Remember, from previously in the notes, we said we can't take the logs of negatives or 0. This is kind of an illustration of that. You see that the inputs into the log function cannot be negative. It also cannot be 0, because the domain of the log function is 0 to infinity. Okay? So let's add this to our base graph list of our base functions that we kind of just know what they look like. If you forget, you can always just graph a couple points on the exponential and then change the x's and y's. Or point plot with a logarithmic function if you want, I guess. All right, so let's graph another one. Let's graph y equals log base 3 of x. Now we don't have to always graph the original every time you want to graph. And actually, to be honest, I'm not sure exactly what the best way to do these are. Different people think of them kind of different ways. I personally kind of, I've done them for a long time, so I kind of know they cross here. I know they have a vertical asymptote here. And I know that next point is going to be, since it's base 3, it's going to be over 3 up 1. Why? Because the log base 3 of 3 is equal to 1. So I kind of just use those 2 points, and you could do the 1/3 here if you want, and graph it like that. Now you guys might be saying, "Well, wait a sec. What? How did you do that? How did you do that?" So let me just kind of go over the other common way to do these. The other common way to do these is to kind of think of the inverse function y equals 3 to the x, and just point plot the 3 most common points: -1, 0, 1, 1/3, 1, 3, right? Where's my pen acting up here? Why has it got that little... whatever. And then just flip around the x and y coordinates. Instead of graphing -1, 1/3, you graph 1/3, -1. Instead of graphing 0, 1, you graph 1, 0. So whatever you guys want to do, either kind of remember the base graph and just do another point, or flip the exponential one around and switch them. Whatever. That's the graph. Domain, 0 to infinity. Range, all reals. Equation of the asymptote, x equals 0. X-intercept, 1. Y-intercept, none. That's it. But of course, we're not just going to graph these base functions. That would be too trivial. We are going to do all the transformations on these that we did on other functions. So let's graph y equals the log base 2 of the quantity -x plus 2. First of all, this is all inside the function. Hopefully you remember that the inside needs to be factored, so you get the transformations right. It kind of depends on the order you do the transformations in, but that's how we did them. -x minus 2. So my base graph is y equals the log base 2 of x. Remember, it's going to have a asymptote down here. It's going to cross at 1. And that next point, instead of being over 1 up 2, it's going to be over 2 up 1, because it's base 2. So 2, 1. So here's my base graph. Don't draw it solid because you have to do the transformations. Now let's identify the transformations. A negative on the inside, that is a horizontal because it's on the inside, and it's a reflection or a flip because it's multiplying by a negative. Subtract 2 on the inside. Normally I would say that's a shift to the left 2, but things are backwards on the inside, so that's going to be to the right 2. So this is a reflection, and this is a translation or a shift. So, and the way we studied in class, we always have to do the flips first. So let's first flip it. So reflect it across the y-axis, reflect it across the y-axis. That gives us this. Something like that, kinda. And then move everything over to the right 2. This point goes over right 2. This point goes over right 2. And most importantly, the asymptote, which was vertical, which was the y-axis, that moves over right 2 also. It's very important that you graph the asymptote on these. Something like that. I think it should be a little steeper. Whatever. No, we're only plotting 2 points, so it's not going to be super accurate, but it's kind of the logarithmic growth, I guess, right? Domain, well, the domain goes from negative infinity to 2 exclusive. Negative infinity to positive 2 exclusive, right? We're picking our x's. We got x's up to here, and then they stop right there, and they're not inclusive. Range, look at the y's, all reals. Equation of the asymptote, vertical line at 2, so x equals 2. X-intercept 1, y-intercept 1. Sometimes we have to do a little bit more work and do some solving and some equations to find those x and y intercepts, but I got lucky with my transformations and I can see those 2 points exactly. Okay? So that's graphing. Now let's pause this or stop this video and we'll talk about some special notations for logs in the next one.